Hello everyone, I am Dr. Sirajullah Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about molecular orbital theory. What is molecular orbital theory? Why we are interested to learn about molecular orbital theory? So in this video, I will answer all such type of questions. So my goal the goal of molecular orbital theory is to describe molecules in a similar way to how we describe atoms. That is, in terms of orbitals, orbital diagrams, and electron configurations. So, I will discuss about the atomic orbitals. You know, my friends, orbital mixing, it is a process. Mixing of atomic orbitals. When atoms share electrons to form a bond, their atomic orbital mix to form molecular bonds. In order for these orbitals to mix, they must having similar energy levels, overlap well, and be close together. You can see in this diagram how two orbitals overlap together. This is an example of orbital mixing. The two atoms share one electrons each from their outer shell. In this case, both 1s orbital overlap and share their valence electrons. Now, molecular orbital sigma bond formations. 1s orbital of one hydrogen, 1s orbital of another hydrogen, forming sigma bond through the overlap create HS sigma bond. You can see in this picture. 1s orbital of hydrogen and 2p orbital of fluorine making sigma bond and formation of HF. Here overlap creates HF sigma bond. Now 2p orbital of fluorine and 2p orbital of fluorine combine together forming overlap create FF sigma bond. Now p orbital atomic orbitals overlap to form sigma and pi molecular orbitals. So px and px combine to form sigma 2p star antibonding and sigma 2p without a star bond. You know, bonding orbital and antibonding orbital have difference in energy. P by p by orbital combine together. It gives pi 2p and pi 2p star. Pi 2p is known as bonding and pi 2p star is known as antibonding. PZ combine together form pi 2p and pi 2p star. Pi 2p is known as bonding and pi 2p star is known as antibonding. So, I will show you one example. And example is ethene, sigma and pi bonds. Let us consider or let us know the set of orbitals. You know here sp2 and plus p. sp2 plus p orbitals. You can see here sigma bonds. And in the second examples, overlap of p orbitals leading to pi bonds. So, set of orbitals x, y, z, you can see how they form sigma bond in ethene and overlap of p orbitals leading to pi bonds. Ethene, sigma and pi bonds. Formation of sigma bonds. Then you can see the formation of pi bonds. Then you can see the space filling models. Now you can see the pi orbitals. So atomic and molecular orbitals. In molecules, electrons occupy molecular orbitals which surround the molecules. The two 1s atomic orbital combine to form two molecular orbitals, one sigma and one antibonding sigma star. So atomic orbitals you can see here combined and forming molecular orbital. One is sigma, another one is sigma star. So if you have hydrogens, so one hydrogen atom has one electron, another hydrogen atom has another electrons. Both electrons combined together, you have two electrons. So you can fill molecular orbitals with electron. So sigma contains two electrons and sigma star has capacity to take two electrons. So two electrons already finish in sigma. So this is the diagram of energy. This is an illustration of molecular orbital diagram of H2. Notice that one electron from each atom is being shared to form a covalent bond. This is an example of orbital mixing. Molecular orbital theory. Each line in the diagram represents an orbital. The molecular orbital volume encompasses the whole molecule. The electrons fill the molecular orbitals of molecules like electrons fill atomic orbitals in atoms. Now, my friends, molecular orbitals and valence bond theory. Electrons go into the lowest energy orbital available. This is through the Aufbau principle. You know Aufbau principle. The maximum number of electrons in each molecular orbital is 2. This is according to Pauli exclusion principle. And you also know Ohm's rule. One electron goes into orbitals of equal energy with parallel spin before they begin to pair up. So you can see the formations of H2 molecules and their molecular orbital diagram. Atomic orbital of one hydrogen, atomic orbital of another hydrogen, formation of molecular orbital, sigma, sigma star. Sigma is known as bonding, sigma star is known as antibonding. Now, how you calculate the bond order? So if you know the bonding electrons or antibonding electrons, you can easily calculate the bond order. So the formula of bond order is equal to number of electrons in bonding molecular orbital minus number of electrons in antibonding molecular orbitals divided by 2. So the bond order is an indication of bond strength. Greater bond order is equal to greater bond strength. The bond order equals the number of bonds formed in the molecule. Predicting a species stability using molecular orbital diagrams. You can see one problem. You can solve this problem, then you will find the applications of molecular orbital diagram. Use molecular orbital diagram to predict whether H2 plus and H2 minus exist. Determine their bond orders and electron configurations. So molecular orbitals of H2 plus and molecular orbital of H2 minus. Atomic orbitals of hydrogen and atomic orbital of another hydrogen. You know, H2 plus does not exist. What is the reason behind it? The reason is one proton have one electrons and another hydrogen have loses their electrons. So there is no electron to pair up. When you calculate the bond order, so half 1 minus 0 become half. So half bond order. H2 minus does not exist. Why? Again, here two hydrogen. One hydrogen have extra electrons, H minus, and another hydrogen 1 electron. So if you calculate bond order, half 2 minus 1 divide, you will get half, means H2 minus does not exist. One question is very common. People always asking these questions, why O2 is paramagnetic, and the paramagnetic behavior of O2 is explained on the basis of molecular orbital diagram. MO diagram for O2. You can see 1s, 2s and 2p. Their molecular orbital sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2p, sigma star 2p, pi 2p, pi star 2p. Now I will discuss about molecular orbital versus valence bond. You know, atoms or molecules in which the electrons are paired are diamagnetic. Those that have one or more unpaired electrons are paramagnetic, attracted to a magnetic field. Liquid oxygen is attracted to a magnetic field and can actually bridge the gap between the poles of horseshoe magnet. The molecular orbital model of O2 is therefore superior to the valence bond model, which cannot explain these properties of oxygen. Now I will show you molecular orbital diagram of HF. You know, here is one hydrogen, one electron, and fluorine have 9 electrons. So fluorine, 1 into fluorine atomic orbital, 2s, 2px, 2py, 2pz and 1s, and 1 into atomic orbitals of 1s hydrogen. So electronegativity of fluorine is greater than hydrogen. So you can see 1s, 2 sigma, 1 sigma, 2 sigma, pi and 3 sigma. So bonding 1 sigma, 2 sigma, non-bonding pi and anti-bonding 3 sigma. So far we have only looked at the molecules with 2 atoms. Now we will see molecular orbital diagram can also be used for larger molecules like CH4. Now here you can see one carbon has 6 electrons and 4 hydrogen, 5, 1, 5, 2, 5, 3, 4 into hydrogen atomic orbital, 1 into carbon atomic orbital, forming methane molecular orbital. Now you can see the MO diagram of methane. Now molecular orbital diagram of H2 molecules, 1 into oxygen atomic orbital, 2 into hydrogen atomic orbitals, forming water molecular orbitals. So MO diagram for He2 and He2. 1 is plus. You know, atomic orbital of helium plus have 1 electrons, here 2 electrons, forming He2 plus. So bond order is half. Another H2, so 2 electrons, bond order is 0. So helium 2 does not exist. Now relative molecular orbital energy level for period 2 diatomic molecules. Molecular orbital levels of O2, F2 and Ne2. You can see sigma 2p less energy than pi 2p. Molecular orbital energy level of B2, C2 and N2. Pi 2p is less energy than sigma 2p. Now using molecular orbital theory to explain bond properties. Continue, you can see here bonding electron loss, anti-bonding electron loss O2 plus. Bonding in S block homonuclear diatomic molecules, lithium 2 bond order 1, Be2 bond order C. In conclusions, bonding electrons are localized between atoms. Atomic orbital overlap to form bonds. 2 electrons of opposite spin can occupy the overlapping orbitals. Bonding increases the probability of finding electrons in between atoms. It is also possible for atoms to form ionic and metallic bonds. My friends, I hope this video will be helpful to you. If you like this video, then subscribe, share my video. Thanks for watching.